All right, let's dive into one of the most incredible stories in all of science. It's about how a 19th century puzzle, a real head-scratcher about electricity and magnetism, ended up completely changing how we see the world and, basically inventing the technology that powers our lives today.
So think about this for a second. It sounds like a trick question, right? One lets you stream movies, one warms your face on a sunny day, and the other lets doctors see your bones. On the surface, they have nothing to do with each other. But stick with me, and you'll see how they're all just different colors of the very same invisible rainbow.
To really get it, we've got to hop in a time machine and go back to the mid-1800s. Back then, physicists were really starting to figure out these wild new forces, electricity and magnetism. They knew the two were connected somehow, but the picture, well, it wasn't quite complete. There was a piece missing.
So here's what they had worked out. They knew for sure that if you run an electric current through a wire, you get a magnetic field around it. Simple enough. And thanks to the brilliant work of Michael Faraday, they also knew that if you have a changing magnetic field, it creates an electric field. You can already see this beautiful symmetry starting to take shape, but it's not quite perfect yet.
And that was the million-dollar question. I mean, if a changing magnetic field makes an electric one, shouldn't a changing electric field make a magnetic one? It just feels right, doesn't it? But there was a problem. The main law they used for magnetism, a thing called Ampere's law, said nothing about it. It was a one-way street.
And this is where our hero, James Clerk Maxwell, comes into the picture. This Scottish physicist looked at the math, specifically at Ampere's law, and realized this wasn't just about making things look pretty and symmetrical. He realized there was a fundamental flaw, a specific situation where the law just fell apart.
And the place where everything went wrong was in a device that seems incredibly simple, a charging capacitor. All that is just two metal plates with a little gap in between. When you charge it, you have a current flowing in the wire towards one plate and away from the other. The question is, what's happening in that empty gap?
This is where the physics just didn't work. According to the old law, if you measured the magnetic field right next to the wire carrying the current, you'd get a certain value. But if you tried to measure it based on what was happening in the empty gap, the law gave you an answer of 0. You can't have two different answers for the magnetic field at the same place. It's impossible. The law was clearly, fundamentally, missing something important.
So, what was it missing? This is where Maxwell had a stroke of pure genius. He came up with a radical idea. He imagined a new type of current, a kind of ghost current that could flow where no electrons could possibly go.
He called it the displacement current. And here's the kicker. This wasn't a flow of physical charges, not like electrons in a wire. No, this was a current made out of a changing electric field. In that empty gap between the capacitor plates, as the charge was building up, the electric field was changing every moment. Maxwell said, that change, that's the missing current.
Now this was a huge deal. It was a completely new way of thinking. He was saying that a magnetic field isn't just created by moving charges. It can also be created by a changing electric field in completely empty space. And when he added this new term, this displacement current, into Ampere's law, poof, the inconsistency vanished. The math worked perfectly everywhere.
And with that final piece of the puzzle in place, the true, beautiful symmetry of it all was finally revealed. Check it out. A changing magnetic field creates an electric field. And now, thanks to Maxwell, we know that a changing electric field creates a magnetic field. They could now create each other, leapfrogging through space forever in this amazing self-sustaining dance.
And this dance, this self-sustaining loop between the two fields, led to a prediction that was absolutely staggering. This wasn't just some neat mathematical fix. It predicted the existence of something entirely new.
When Maxwell took all four of his now complete equations and put them together, they described a wave. Not a wave in water, not a wave of sound, but a wave of pure electric and magnetic fields that could travel through the total vacuum of empty space, all on its own. An electromagnetic wave.
But that's not even the most shocking part. The equations didn't just say these waves exist. They predicted their exact speed. And when Maxwell plugged in the fundamental constants of electricity and magnetism and calculated that speed, he got this number, 300 million meters per second.
You have to imagine him just staring at that number, because it was an incredibly familiar number to every physicist alive. For years, people had been trying to measure the speed of light, and their best measurements were all clustering right around that exact same value. The conclusion was just inescapable. Light itself, the very thing we use to see.
It's nothing more and nothing less than a ripple in electric and magnetic fields. In one single beautiful theory, Maxwell had tied together electricity, magnetism, and optics. It was one of the greatest unifications in the history of science.
And this is what one of those waves looks like. You've got electric fields, say, oscillating up and down. That changing electric field creates a magnetic field that oscillates in and out. And that changing magnetic field then creates a new electric field a little further on. They're constantly creating each other, always at right angles, hurtling through space at the speed of light.
But Maxwell's theory did more than just explain visible light. It predicted a vast, unending spectrum of these waves, a whole invisible rainbow stretching out way beyond the colors our eyes are built to see.
And here it is, the electromagnetic spectrum. It's kind of mind-blowing, right? Radio waves, microwaves, the infrared that your remote control uses, all the colors we see, even ultraviolet, X-rays, and gamma rays, they are all the exact same thing. They're all light. The only difference is their wavelength.
Just think about a microwave oven. It's Maxwell's equations in a box. It generates electromagnetic waves at a very specific frequency, one that's perfect for making water molecules shake like crazy. That shaking is energy, which we feel as heat. And just like that, a purely theoretical idea from the 1800s is heating up your leftovers.
And really, it's no exaggeration to say that the world we live in today is built on this discovery. What started as a purely abstract thought experiment completely unlocked a technological revolution.
I mean, look at that journey. It started with a tiny abstract math problem about a capacitor. That little itch led to this grand, beautiful, unified theory of nature. And once we understood that theory, we could build technologies based on it. And that's where we get radio, television, cell phones, Wi-Fi, pretty much any technology that sends information through the air without a wire.
And it all came from just asking why. Why wasn't this law symmetrical? Why did the math break? Maxwell showed us that beneath the surface of reality, there are these incredible hidden connections. He tied electricity, magnetism, and light together. Physicists today are still searching for even deeper connections. It just makes you wonder, doesn't it? What other invisible rainbows are right there in front of us, just waiting for someone to ask the right question?